Yes, good evening to all my faculty colleagues and students. It's going to be the third visual treat or an online treat as part of the chemical engineering lecture series that we have initiated in this semester to make sure that you have a holistic learning beyond the course curriculum. I'm very happy to welcome the speaker of the day, Dr. Vikram, a senior chemical engineer from Eastman Chemical Company, and also an alumnus of Sastra, a gold medalist 2007 batch. The Associate Dean, Dr. Ponuswamy, the coordinator of the event, Dr. Rangabashya, my faculty colleagues, Dr. Alagation, and others who will join in a few time, and also all the students. With this, I would request Dr. Ponuswamy to give a short welcome note of the talk and of the program at large. Yes, sir. Over to Ponuswamy.
Good evening, one and all. It's my pleasure to welcome today's speaker, Dr. S. Vikram, faculty colleagues, and my dear students for the third lecture of this chemical engineering lecture series. As you know, we have taken this initiative to sustain our regular association activities, which includes conducting guest lectures from external experts from industry, academia, without break. So in a way, we need to thank this lockdown, as now we are able to hear from people who are from various remote places. Today's guest also from USA. So the boundary has been broken now as we move to online. I wish we continue this in the future also to get the best for our students. My special thanks to Dr. Vikram. I think it is early morning there in Pittsburgh, around 6:30 a.m., right?
Yeah, 6:30.
So when we approached Vikram for the talk, he readily accepted in spite of his odd timings. Thank you, Vikram. So Vikram actually graduated from Sastra University in the year 2007. He was my one of the favorite students, which I should say. So he did his BTech projects under my guidance. He was very sincere, hardworking, and dedicated student. Those days, actually, we did not even have the research labs like what we have today, and he managed very well to do his work in the academic lab itself and got excellent results that could be published in Journal of Biomass Material, which is one of the leading journals in the field. So that actually tells you about his quality of work also. And coming to this lecture series, nothing, needless to mention that we are organizing this lecture series, and this takes a lot of effort from various people. Thanks to Dr. Rangabashya, who has taken this task, and other fellow colleagues who assist him in this process. I request all students to actively participate in this lecture series without fail and make this initiative big success. So I am excited to hear from Vikram now. Yeah, over to the question.
Sir, so that set the stage for the students to have such an opportunity to learn from experience of people at different walks of life. Now, with this, I would request Dr. Rangabasham, the coordinator of the event, to introduce the speaker formally for the day and set the stage for his talk. Dr. Rangabasham.
Yeah. Good evening to one and all. Our today's speaker, Dr. Vikram, completed his Bachelor of Science in the Department of Chemical Engineering, Shastra Deemed University in the year 2007. Master of Science in the Department of Chemical Engineering from Indian Institute of Technology, Madras in the year 2009. Obtained Doctor of Philosophy in the Department of Chemical and Biomolecular Engineering from North Carolina State University in the year 2014. During his PhD, he worked on other discipline of research works and in master's project, and in undergraduate project also he contributed, assisted with many other research projects as well. Regarding patent, he obtained on ion catalyzed transfer hydrogenation of esters to alcohols. Regarding publications, he has published 6 research articles. The first one started under the affiliation of Sastra deemed university in one of the most important and challenging journal, the Journal of Hazardous Material, followed with combustion theory and modeling journals, combustion and flame, proceedings of combustion institutes, the Journal of Physical Chemistry A, Catalyst Today. So these are the journals. He had publications. He attended many international conferences as well in the AICHE meeting. And with respect to the awards and scholarships, he obtained the fellowship, the Foundation of Molecular Modeling and Simulation in the year 2012, inducted in Chemical Engineering Honor Society Omega Chi Epsilon in year 2011, Ministry for Human Resource Development, Government of India, scholarship for postgraduate students, Ulapati Sri G. Shesha Iyengar Award for securing first rank in BTech Chemical Engineering in the year 2007, Best Outgoing Student of Chemical Engineering Department in the year 2007, Dean's List for being on top 2% of the batch 2004-2006, scholarship for being the top 10% in the year 2003 and 2004. Then the certification, IBM Data Science Professional Certification through Coursera in the year 2019, Adhesives and Seal and Counts Training Academy Certificate Program graduate in the year 2018, Six Sigma Green Belt from Eastman Chemical Company in the year 2017. So, in the undertake of projects in the Eastman Chemical Company, he worked on many manufacturing and process engineering related projects, as well research and academic projects. He has joined as a research intern in the May 2014 in Eastman Chemical Company, and now working as a senior chemical engineer in the Eastman Chemical Company. And he performed with Six Sigma Green Belt certification with proven cost-saving projects of more than $500,000. Thank you. Now I request Dr. Vikram to take over the session.
Okay. So should you have to unshare your screen for me to share?
Yes.
Yeah.
Yes.
Yes.
Let me know once you see my screen.
Yeah, you can share the screen. It is getting presented.
Okay. I really thank Sastra University for providing me this opportunity, and I think this is a wonderful opportunity. I hope all of you are staying safe, healthy, and COVID-19 has weirdly presented this interesting opportunity to present from US to India, which otherwise would have been a lot more difficult. And I don't know whether it's a fortunate or unfortunate situation of COVID, but there are some bright sides to it, I guess. So with that, I'll go ahead and start with my talk. So my talk is on pyrolysis kinetics of biomass-related compounds. So first off, I wanted to let you all know that these slides might contain a lot more chemistry than chemical engineering, but I'll emphasize the importance of where knowledge of chemistry is important in a chemi industry as well as in academia as well, so that kind of relate to that. Not everything is just fluid mechanics and thermodynamics. There is also chemical kinetics portion involved in a lot of processes. So during my PhD work, I had focused on kinetics of several different topics, such as combustion of oxygenated fuels, combustion of large hydrocarbon fuels. I was also focused on pyrolysis and pyrolysis chemistry, of glucose and cellulose. So I'll be focusing this particular talk on glucose pyrolysis and its implication on biomass pyrolysis. So the terminology pyrolysis means that you are heating up something largely in the absence of external agents. The only energy supplied to the material is heat, and the molecule or the material breaks down due to that energy. So we'll try to figure out what happens when you heat cellulose or glucose, and in the presence of heat, what all chemistry happens in the process. So in this slide, we have what we call biomass. So there are different types of biomass. It can be from plants, it can be from paper waste, it can be from animal waste, and all those things. So in this particular talk, we'll be focused on what is called as lignocellulosic biomass. So what it means is the biomass contains a significant portion of lignin material and a significant portion of cellulosic material. So cellulose is actually a oxygenated hydrocarbon. I'll show pretty soon what it looks like, but this is like a typical composition of what lignocellulosic biomass would have. So the first question is, what is the importance of pyrolysis of biomass? So in this stage where we are trying to find out ways to make renewable energy and use other forms of energy, the question arises as to, can we use fuel that is derived from plants as a source of for like gasoline or something like that? So question as to whether I can break down biomass and make useful fuel out of it. So that was kind of the motivation to do research on this particular area. And in this particular talk, I'll be talking mostly about how glucose breaks down into smaller molecules and what kind of implication it has on the on cellulose pyrolysis. So when you look at, I'll spend a little bit on this particular slide because it's kind of the it sets the stage for the rest of the slides that are going to follow. So if you have any questions on the way the molecule looks like and stuff like that, please stop me and ask at any time. So you can see here, cellulose is a polymer that is actually consisting of oxygen, carbon, and hydrogen. And it's a polymer that the most basic functional unit of cellulose is beta-D glucose. And it's a 6-membered ring with one of the members of the ring being oxygen. And it has alcohol groups at every other position. And each of this beta-D glucose chain is linked by what is called as a glycosidic linkage. So this is the carbon-oxygen-carbon bridge that keeps the cellulose molecule intact. So this is what it's polymerizing around. So when we started this research, we were trying to look at what were the existing model that describes how cellulose pyrolyzes. So one of the first models was a very simplistic model, which said cellulose basically decomposes into some volatile material and some char and gas form, and we were trying to get some experiments and try to fit it with a model that fits this reaction scheme. And with time, the model started becoming more and more detailed and slightly more and more complicated. It started to explicitly describe some specific products in the product stream. So for example, I'll talk a good bit about levoglucosin that's actually shown in the slide as one of the major chemical pathways. One of the most recent ones during that time was an article in JPhysChem C, where they were talking about a lot of chemicals that they saw using gas chromatography, mass spectrometry. They were able to identify a lot more specific compounds coming out of cellulose pyrolysis. But even during then, there was no good understanding of how each of these chemicals were formed from cellulose. So these are all largely empirical in nature, and they were trying to do experiments and fit some kinetic parameters to this scheme. So in this work, what we intended to do was to get a little bit more detail into how the chemistry happens at a fundamental level. So when I say fundamental level, so for students in this call, you would have heard about elementary reaction step in chemical kinetics course. So if this term looks new to you, it's about time you go back and start looking at what chemical kinetics has to offer. And so we'll try to understand each reaction step using an elementary reaction model, and we'll try to use quantum chemistry to calculate rate parameters and try to find out how the reaction progresses in the reaction landscape. So for this work, we'll use what is called as transition state theory, which is also a term that you would often see in chemical kinetics textbook. So what transition state theory describes is when a reactant converts to a product, it goes through a hump. So the energy required for the reaction keeps going up, and it crosses a point where it falls down the potential energy landscape to become a product. So this intermediate state, which is highly unstable, is called a transition state. And there are ways to find out what the energies of each state are, and methods to calculate the rate coefficients based on this transition state theory. With that, so we'll dive into the problem at hand here, trying to understand cellulose pyrolysis kinetics. So first off, as I mentioned in the slide before, cellulose is a fairly large molecule, and so quantum chemistry calculation is a pretty involved calculation where you solve some kind of a modified Schrodinger equation to make sure you calculate the energy and vibrational and rotational frequencies of molecule. And as the number of atoms in this calculation increases, it quickly becomes a lot more difficult, and you would need several processes to actually even calculate the energies of cellulose molecules. So what we wanted to do was simplify this problem a little bit. So if you are in the so an analogy is, if you are in the right street, you can probably find out the address of the house much easier instead of trying to have a very detailed zoomed in Google Maps, for example. That's like kind of a non-chemical engineering analogy for what we are trying to do here. So what we try to do was, instead of working with cellulose, we simplified our analysis to glucose, so that we can figure out how glucose reacts and extrapolate those understanding to cellulose. That was our strategy to understand cellulose pyrolysis. So the first thing we did was we took some recourse on historical work that has been done. So one of the seminal works that was published in pyrolysis journal was by Edward Sanders. So he had looked at these were not elementary reaction chemistry. This was largely trying to map out potentially from what's the source of a particular product and how each of these products might have been formed. This was like a hypothetical schematic, but it was one of the closest to elementary reaction steps that were published in the past. And first off, I'll focus on this particular reaction. So glucose, alpha or beta glucose becoming a product called levoglucosin. So levoglucosin is a molecule that's formed by dehydration of glucose. So glucose will lose a water molecule during the course of reaction to form levoglucosin. So this is the focus of my talk today. So trying to understand what chemical pathway from beta D glucose leads to levoglucosin, and how it relates to cellulose chemistry. So the first reason why levoglucosin is important in cellulose pyrolysis chemistry is when you see the amount of levoglucosin formed when you pyrolyze each of these molecules, we see that cellulose, the yield of levoglucosin in cellulose is much higher than in the dimer form of glucose compared to glucose itself. So as the polymer length increases for cellulose, you will see a lot more levoglucosin come out as product. So that's why it's one of the important chemical pathways to understand to really know what's going on with cellulose pyrolysis. Apart from that, when you look at glucose itself, since it's a single monomer molecule, it can not only make levoglucosin, but it can also open up to linear forms such as beta D glucose and also alpha D glucose, which is like the inverted cyclic version of beta D glucose. So first things first. So glucose can actually exist in different conformation, and I refer to it as char beta D glucose. So it's a conformation where it's fairly spread out in terms of atomic locations. So this is one of the stable forms of beta D glucose, and it can. The first thing that can happen to cellulose is when you heat it up, it can bend around and make different conformations of beta D glucose. So in this slide, I show a boat form and an inverted chair form, which is basically the bending of the carbon oxygen carbon bond to form different structures here that's shown. And the second reaction that can happen, as I mentioned in the previous slide, is linearization of this glucose. So it can open up the cyclic ring to form a linear structure here, which is called D glucose. So this opening up helps in converting to different conformations as you heat up. So inverted chair form can convert to a regular chair form or a boat form. In fact, it can also rotate at one of the carbon positions to form alpha D glucose. So these are some of the reactions that can just happen with beta D glucose. And this conversion of char to beta to alpha form is called as a mutarotation. So what really happens here is the location of the OH group and H group that I've shown in green color star here can happen when it goes through the linear form. So that's called mutarotation. So that reaction, it doesn't happen by just rotating the hydrogen and OH bond. It has to go through a linear structure to switch from alpha to beta form. And so before I delve into the formation of levoglucosin, first of all, I wanted to ask if there is any questions from students, or am I still audible at the very least, to make sure I'm...
Yeah, you are audible.
Okay.
No issues. Try.
Okay. So
yeah, you can continue. Yeah.
Sounds good. So before I dive into levoglucosin chemistry, I would like to make sure we understand the nomenclature of how we are trying to label each of these atoms, so that it's helpful to visualize how the chemistry happens. So as shown here, I've labeled carbon number from 1 to 6. So glucose is a 6-carbon molecule, and anytime I refer to carbon number 1, that's the C1 in this particular schematic, and the numbering is kind of in the clockwise order from 1 to 6. And every oxygen attached to a particular carbon is numbered the same way. For example, oxygen attached to carbon number 1 is referred to as oxygen 1, and hydrogens connected to that oxygen is referred to by the same number, like hydrogen 1 would be the hydrogen connected to oxygen number 1. So this might seem lame, but this numbering is important to keep track of what is happening, because it can become complicated way too soon. So in terms of glucose, you also have other effects going on, such as hydrogen bonding. So some of the oxygen molecules are in oxygen atoms are in very conducive location for facilitating this hydrogen bond, which also impacts your kinetics. So hydrogen bond can either help in reducing the activation energy of a reaction, or it can actually contribute to increased activation energy of a reaction. So these are pretty important effects in a very oxygenated molecule such as glucose and cellulose. And in this particular talk, so I'll be focused on carbon number 6, oxygen number 6, carbon number 1, and oxygen number 1. So keep up with me. If something gets confusing, please stop me and ask me questions, and make sure you are able to understand what's going on. So as I said, levoglucosin is a molecule that's formed from glucose by a reaction called dehydration reaction. So there are two ways in which this dehydration reaction can happen. So in the dotted line here, I have shown 4 atoms that are involved in this reaction. So on the left-hand side, you can see hydrogen number 6 moving towards oxygen number 1 and leaving as water, and oxygen number 6 attaching to carbon number 1 to form levoglucosin. Another way this chemistry can happen is hydrogen number 1 can leave along with oxygen number 6 and complete a cycle with reacting with carbon number 6. So C6 and O1 can form a bond, and O6 and H1 can form a bond to leave as water. So this is where my PhD life kind of started. So a funny anecdote here is that, so when I first drew out this particular reaction to talk to my advisor about how I think levoglucosin can be formed, the first thing he mentioned was, so the way the reaction is constructed, it has 4 atoms involved in it. So it's called a 4-centered pericyclic reaction. There is a rule in organic chemistry called Woodward-Hoffmann rule, where it says a 4-centered reaction, a reaction involving 4 atoms are thermally forbidden and photochemically allowed. So if you don't understand what I'm saying, I was the same way 10 years ago. So I didn't have a clue of what he was talking about. So so he said this reaction is probably, so what it actually means is this reaction is very hard to happen. In a 4-centered reaction would have a lot more activation energy to happen. So he said it would probably not be a worthwhile time trying to figure out if this reaction happens at all. So as a logical next step, I went ahead and tried it anyways, and it turned out it actually worked. And both of us were kind of surprised that this didn't follow a classical chemical rule where 4 atoms reacting here by a bond formation and bond breaking was actually thermally allowed, and it was not forbidden by the Woodward-Hoffmann rule. So we wanted to kind of understand a little bit more deeply onto what is going on here. So before that, I'll point out what the activation energy of both of these reactions are. So both of these are 4-centered reaction. One had a 46 kilocals per mole of activation energy. The other reaction on the right hand side had a 74 kilocal per mole of activation energy. So the reason why I point that out is, to give you a realistic scenario, a reaction that has somewhere around 46 kilocalories per mole of activation energy can happen pretty reasonably at elevated temperatures. A reaction that has 74 kilocalories per mole is, when you compare the rate of reaction, so for chemistry students here who understand Arrhenius rate equation, the activation energy is kind of the exponential term that goes into the Arrhenius equation. So e to the power minus EA by RT, right? So for every kilocal per mole of activation energy, you are exponentially making the reaction harder, is what that means for the same temperature. So a 25 kilocalories per mole or 20 kilocalories per mole of activation energy difference is a big deal, because it determines that one pathway is a lot more feasible than the other pathway. And so for that reason, we think a reaction does not happen by eliminating oxygen number 6 and hydrogen number 1. It rather happens by eliminating hydrogen number 6 and oxygen number 1. So I'll pause right here and ask as to if I was still legible and if people are still able to follow to some degree.
Yeah. Yes, Vikram. Yeah.
Okay. So any questions so far?
No, nothing. We will.
Okay.
It may take some time for the students to sync at the undergraduate level and then come to your level and ask the questions.
Okay. So, if you didn't pick up anything from this talk, for the students, I would emphasize that understanding chemical kinetics and thermodynamics is of importance if you want to either become a chemistry researcher or even in an industrial setting to understand the processes. A good grip on chemical kinetics and thermodynamics would help. So I wanted to point that out as I go through this slide. So going forward, we wanted to try to understand why there is such a significant difference between one particular pathway compared to the other. So after working on it for a while, we figured out the following. So even though this reaction says it's a 4-centered reaction with 4 different atoms here, it is in principle a 6-centered reaction with the lone pair electrons on oxygen contributing to the reaction. So as you all know, oxygen and atoms like oxygen and nitrogen, they have what is called as a lone pair electron. That's what makes their structure not tetrahedral. So they are slightly different from tetrahedral structure compared to, if you compare water, ammonia, and methane. Methane is a tetrahedron, whereas water is like a angular planar bond, OH. And the main reason why these are distorted is because of the lone pair effect. So what we found in this particular case was these lone pair electrons also play a major role in this reaction. So the process of the lone pair electrons interacting with this reaction kinetics is called as delocalization. So if you take the reaction on the left-hand side, what is really happening is the lone pair on the oxygen number 6 and oxygen number 1 is delocalizing into the anti-bonding orbital of the O6H6 bond. So to make the terminology simple, so whenever you populate your orbital diagram in your anti-bonding level, so that bond loosens. If you're populating it in the bonding orbitals, your bond strengthens. So that's kind of a simplistic way of saying what's going on here. So the lone pair electrons start to delocalize in the antibonding orbital of O6H6 bond, weakening that bond way more than what it usually would take, and thereby making the formation of water much easier, and formation of O6C1 bond much easier. Whereas if you see for the reaction on the right hand side here, the antibonding orbitals are delocalized into the places where you would actually like to form a bond. In this particular case, you would like to form a bond between C6 and O1, and your delocalization of electrons happen in the C6O1 bond, making it a lot more difficult for the reaction to progress. And that is the reason why you have about 20 kilocalories more energy required for the reaction happening on the right hand side compared to the one on the left hand side, even though they actually make the same product. So in effect, what happens here is the hydrogen number 6 attached to oxygen number 6 leaves from glucose to form water, and the O6C1 bond happens to form the molecule called levoglucosin that I described. So instead of going into deep physical organic chemistry here, the other way to say the same thing is, so we did some simulations. Instead of using levoglucosin, instead of using oxygen at a particular location, we replaced it with nitrogen and carbon. So in this particular case, whatever you see in blue color, unless you are a colorblind person, so the ones in blue color is nitrogen, and the ones in gray color is carbon. So I have also noted down the activation energy of each of these reactions here. So what we notice right off the bat is, if you replace the oxygen O1 with a carbon instead, your activation energy is 109.6 kilocalories per mole instead of 45. So if you have to, so let's take for example methanol, which is CH3OH. If I had to break the oxygen hydrogen bond, it will take about 104 kilocalories per mole. So that's like taking a hammer and breaking a molecule instead of trying to find another easier way to form a bond. Similarly, if you took ethane, for example, CH3CH3, so the breaking the carbon hydrogen bond takes about 100 kilocalories per mole of energy. So if you look at the activation energy for the formation of the one on the bottom right hand side, where we have replaced oxygen with carbon, that's pretty close to the bond dissociation energy of carbon hydrogen bond. What it signifies is, so that's not, first of all, a feasible reaction. Secondly, the way it's happening is a pretty rough way, where you're physically pulling out one of the hydrogen from carbon, which is taking about 100 kilocalories of energy, and trying to force it on the other carbon, which is also contributing to some energy before it leaves out as methane. Whereas when that molecule was oxygen, it happens pretty naturally. And as I pointed out in the previous slide, the main reason for that to happen is the existence of lone pair electrons in oxygen and nitrogen, and there is no lone pair electron contribution from carbon. So that's why you see a very significant difference in the way the reaction occurs here. And so my advisor was correct in that if this molecule was carbon, this reaction would have been thermally disallowed, and you would not have seen a four-centered reaction happen with carbon instead of oxygen. So this was kind of a confirmation as to why we see a lot more levoglucosin when we see glucose or cellulose pyrolysis. So the next thing that is important to us is, once we understood how glucose pyrolysis, remember our main objective was to understand cellulose pyrolysis, and we we try to make a simplification by approximating cellulose to glucose. So it's about time we went to understand what cellulose pyrolysis means to the glucose pyrolysis. So what we did here is we took out the hydrogen at number 1 position here and replaced it with methane, methyl group, ethyl group, and isopropyl group. So we tried to understand how much difference in activation energies if you actually started building more molecules around the hydrogen number 1. And what we observed was there was no significant increase in activation energy if you actually replaced the hydrogen number 1 with much heavier group, functional group like isopropyl or even a glucose molecule. So that was an encouraging result because you can now start approximating cellulose by making this group in circle heavier and heavier. So that's kind of a direction towards understanding cellulose pyrolysis. The other thing that we wanted to study related to cellulose pyrolysis was the effect of the alcohol groups present in glucose and how it can potentially help the formation of levoglucosin. So, for example, if you take two different cellulose molecules, can the hydroxyl groups from one cellulose molecule help the levoglucosin formation in another cellulose molecule? So in the schematic I've shown here, what we have tried to understand is if we had a external water molecule, can water molecule act as a catalyst where it donates one of its hydrogen to the leaving oxygen group and pull off one of the hydrogen from the glucose in the structure to form levoglucosin. So in effect, the external water molecule takes a hydrogen, gives back a hydrogen, and helps in the formation of levoglucosin. And we did find that the activation energy reduced by about 8 kilocalories per mole if there was an alcohol group trying to catalyze this reaction from the outside. And as the size of the alcohol group increased, like for example, from water to methanol to ethanol to isopropanol, the activation energy started going down. So what it means for cellulose pyrolysis is as I increase the functional group attached to the external alcohol, it actually facilitates the formation of levoglucosin. And as I said, the implication for cellulose pyrolysis is that based on the same logic, we can extrapolate the fact that the levoglucosin yield would be much higher in cellulose pyrolysis compared to cellobiose compared to beta-D glucose. So in this particular case, cellobiose is the dimer of beta-D glucose. So I forgot to mention what cellobiose meant, but it's the dimeric form of beta-D glucose, and the polymeric form is cellulose. So in terms of cellulose pyrolysis, what it means for us is we will have this hydrogen number 6 go with oxygen number 1 and oxygen number 6 forming a bond with carbon number 1. And you can recognize that this can happen anywhere inside. So it doesn't have to be the end group of cellulose. It can be anywhere in between as well. And it can break off as levoglucosin. That's why you see a lot more levoglucosin form in cellulose pyrolysis compared to beta-D glucose, because beta-D glucose also has this option of becoming a linear molecule, whereas cellulose cannot. So if this reaction happens anywhere inside the polymeric chain, it cannot linearize at that position. It can only form a cyclic molecule there. And as I said, there are several alcohol groups in cellulose, so it can potentially act as a catalyst for aiding this bicyclic reaction for the formation of levoglucosin. So and you can have this reaction at any position. So that's why it facilitates higher yield of levoglucosin in cellulose pyrolysis. And several OH groups here can actually catalyze the biomolecular reaction that I mentioned, where alcohol group is assisting your levoglucosin formation. So I'll actually have put a fun fact here. So if you have a forest fire or something like that, one of the markers that's used to detect a forest fire is levoglucosin. So your cellulosic material that's burning in the forest fire is actually a pretty strong molecule that can be detected using a spectroscopic analysis, and that's what is a useful detector for figuring out if there's a forest fire or not. So I learned it after the fact doing this project. So I thought I would share this with the group here. So when going back to glucose pyrolysis, there are other reactions that happen apart from levoglucosin formation. As I mentioned in the first slide, so it can isomerize to a linear form, or a 5-membered ring, or a 6-membered ring with the OH and H group inverted. So these are all possible reactions that I will not go into in this particular talk. We also, the specific reaction that we looked at was the reaction from beta D glucose to levoglucosin that we covered in this particular talk. And in your industrial organic chemistry, you would have learned a reaction called Aldol condensation, where alcohol and aldehyde reacts to form a bigger aldehyde. So that's retro-aldol condensation, means the reverse of that. So it's a reverse aldol condensation, where a bigger aldehyde or ketone breaks into a smaller alcohol and an aldehyde. And another reaction is called keto-enol isomerization. So it's also called tautomerization in chemistry. So enol, where there's an alkene and an alcohol group, isomerizes to an aldehyde or a ketone. So that's called tautomerization, and that's another reaction that can potentially happen here. And there are other 6-centered reactions that can break and form molecules like formaldehyde and glyceraldehyde and stuff like that in this particular case. So after we published this work, there was still an existing question as to whether whatever I spoke here so far comes under the classification called concerted reaction. So you have bonds forming and bonds breaking in a very synchronous manner simultaneously. That's called a concerted reaction. A radical reaction or a free radical reaction, on the other hand, means that you have a bond breaking by a homolytic fission, meaning if you have, say, carbon hydrogen bond, so they are forming a bond by sharing an electron. So when the bond breaks, each of them takes away their own electron, and now they are a very reactive molecule. So that's called a radical chemistry. So there was a question as to whether cellulose pyrolysis happens by a concerted reaction or a radical mechanism. And we performed other experiments that I don't talk about in this particular slides, where we found both of them are possible, and it really depends on what reaction conditions you have. So at low temperatures, less than 400 degrees or so, concerted reaction is favored, and you would see a lot more of levoglucosin and other molecules forming, versus if you heated it up far greater than 400 degrees Celsius, you'll start forming free radicals that can aid in other reactions, where you are pulling off beta scission reactions and stuff like that, so which I won't talk about in this particular talk. So in summary, we try to understand how cellulose pyrolysis happens based on our investigation using glucose as our test molecule. And we think we did a fair job on trying to extrapolate some of the understanding from glucose pyrolysis all the way to cellulose pyrolysis. we found that there is a chemical pathway that has about 46 kilocalories per mole of energy that forms levoglucosin from glucose, and the activation energy is pretty similar for cellulose to form levoglucosin as well. We also found that the alcohol groups in glucose and cellulose can catalyze the formation of levoglucosin. We also found that the levoglucosin formation itself is a concerted reaction where there's a simultaneous bond making and bond breaking, and there are several reactions in the glucose pyrolysis and cellulose pyrolysis reaction step, which are concerted reactions in nature. And this work had been done about 7 years ago, and the latest publication we had was 4 years ago. And since then, there are a lot of evidences out there in the literature that suggests that concerted reaction and the assistance of alcohol groups are indeed the ones that explain formation of a lot of these molecules that we see in cellulose pyrolysis. And we also saw that glucose can isomerize to linear or 5-membered rings as well, which explains the formation of some of the furanic molecules in the cellulose pyrolysis. And the way it ties up with cellulose pyrolysis is cellulose can break into smaller cellulosic chains and also form this bicyclic ring in the end group. So I think there's a lot more work that can be done here, and for students listening to this talk, if you're ever interested in this particular area, you can feel free to talk to me at any time. And with that, I would like to close this talk and open it up for the floor to discuss this topic.
Thank you, Dr. Vikram. Yeah, Vikram?
Thank you. Hello, yeah.
Yeah. So there are two questions. So first I would take the question of our faculty and R.S. Saravanan, right? You can see in the chat box, I'll just read. Does the presence of inorganic ions in biomass actually interfere with levoglucosin formation?
Absolutely, yes. So after our work here, there was a couple of work from another group that looked at presence of sodium ions and other 1+ ions that can actually interfere with the formation of decomposed pyrolysis of cellulose. Yes, and some of them can be reactions that help in the formation of levoglucosin. Some of the ions are detrimental to this reaction. Yes.
Okay. Yeah, Dr. Saravanan, you want to ask anything? Okay, yeah, thank you. So the next question is from Dr. Rangabhashan. The question is, in case of various biomasses sourced from lignocellulose, the percentage distribution of lignin, cellulose and hemicellulose are almost in the similar range. Mm-hmm. Under such conditions, how about the control factors over the production of pyrolytic products?
So when we started this research, diving directly into looking at biomass pyrolysis, which is a complicated mixture of lignin, cellulose, and hemicellulose, was a fairly difficult task. So we kind of isolated cellulose as a pyrolysis topic by itself, and there is ongoing research work on what happens to lignin when it pyrolyzes, what happens to hemicellulose when it pyrolyzes. So I think the idea of putting it all together under one framework where we have all the reaction mechanisms for cellulose, hemicellulose, and lignin together, and certainly the interaction of these components with each other is still underway, and it's not very clear how this interaction happens. Does that answer your question, Dr. Rangabhashan?
Yeah, thank you. Thank you. Thank you.
Okay. So Dr. Vikram, now this is from the student's end. So I'm just assuming myself to be student, and I want to put very layman questions. So how are these activation energies that you showed estimated? Are they like computational thing or like experimental value?
So the activation energies that I have here in this particular slide are computational in nature. So we use what is called as transition state theory. So
Okay.
there are quantum chemistry methods to calculate the energies of heat of formation of a particular reactant, heat of formation of product, and heat of formation of transition state. So if you subtract your heat of formation of transition state with reactant, that gives you the activation energy. So what your quantum chemistry will give you is vibrational, rotational, and translational frequencies of particular molecule. And you can use statistical mechanics where you calculate what is called as partition function to calculate your pre-exponential coefficients, and also heat of formations would give you the activation energy.
Okay. So in this continuation of the same, so if that is the case, how these values cope up with like experimental values? I mean, is there a way to check these values? Because in simulations, it's more of an native environment or a virgin environment, but that will not be the case in case of experiments.
Right. That's a very good question. So the activation energy that we had before we had more experiments in this particular field, we were trying to compare it with the activation energies that were reported in experimental work in literature, and trying to kind of see how close we are to the levoglucosin formation step right here. Are you able to see my screen? Just want to make sure.
Yes. Yeah.
Yeah.
The screen is visible.
So this activated cellulose to levoglucosin step was some of the experimental numbers we had to compare at the time. But after we did this research, there were more papers coming out that specifically looked at the levoglucosin formation by using molecules like cellobiose and cellotriose, and they used other test molecules like dextrins and stuff to find out, to estimate what the activation energy is, and it turned out we were pretty close to what is experimentally found.
Okay, yeah. So that's nice. So yeah, there's a question. I'll just take the student question now. The question is from Rajeshri, third year. How in the molecule specific atoms are replaced or changes or removed? If 1 mole of cellulose is subject to these changes, do every molecule undergoes the same change?
So I'm assuming the student is talking about this particular slide. So
yes,
it was a theoretical exercise. So this was not a real experiment that was conducted. So we tried to replace the oxygen here with nitrogen by simulation and try to calculate the activation energy. So this was to understand why we are getting this weird, really low activation energy compared to like a homolytic bond cleavage that's shown here. So as I said, we didn't really perform this experiment. This was an exercise to understand why levoglucosin has much lower activation energy.
Okay, so I hope. So she has a follow-up question also. What are the other applications of levoglucosin?
So as I said, levoglucosin is a marker for forest fires, and at least in the United States, it seems to be like a more frequent ordeal now of forest fires in California. So can potentially be a way to detect forest fires. Apart from that, in terms of making fuel, this is not a molecule of interest for you. So levoglucosin is a major product formed in this particular case. That is the product you want to suppress. So you don't want this reaction to actually happen. So understanding this chemistry allows you to find ways to suppress this chemistry and boost other chemistries that will form smaller molecules that are more relevant to making fuels or other useful chemicals from the glucose or cellulosic products. So I know that's not a very good answer, but this is basically to try and say we need to understand everything in this pod theory to understand how to manipulate your kinetics to suppress one chemistry and enhance the other chemistry. So it's kind of a pathway to that.
Yeah, thanks. So you have essentially made the student to think, so they can now go back, think, find. So there's another question from a student, final year, Kumaran Nagapan. The question is, glucose is a monomer, right? How are the results, I mean, conceptually, if I understand this question, the glucose reaction studies are extended to cellulose. So that means will glucose and cellulose, which is actually a polymer, will behave in the same way, or it should be like independent?
So when you have glucose, you have other reactions that can happen. So for example, you go to the slide here. So glucose can open up into linear molecules and 5-numbered molecules and things of this sort. Whereas if you look at cellulose, it cannot form a linear molecule or a 5-membered molecule by breaking up right here. So it is kind of constrained to forming like a ring a depolymerization reaction where we form a Levoglucosin bond here. So in that aspect, the work on glucose extends to cellulose by certain similar chemistries. We can also extend the work of glucose to cellulose by saying there are certain chemistries that would not happen in cellulose, mainly because of the fact that one is a monomer and the other one is a polymer. So having this polymerase structure forbids it from going through many of these reactions that are shown here. So that's kind of an extension of how cellulose pyrolysis would behave based on glucose reactions that we study.
Okay, yeah, thank you. So I'll take one more student question. So this is a pretty long question. I hope to have conveyed. This is from Venkatanathan, a third-year student. He says, like, if you have external OH groups, the OH groups that are outside in the periphery act as a catalyst for the reaction to them. And bigger the molecule is, I mean, bigger in the sense probably means the distance. Okay, the activation energy comes down. I mean, like he has made this inference from the molecular structure or the size that you have actually shown. Yeah, so now he is asking, I think, yeah, sorry.
Yeah,
so, and I hope you read the question?
I'm reading the question as is. I have the question also on the side. So
probably he's seeing that the size, and he says that means there is some other factor towards this reduction of this activation energies, and like he has put a Pandora's box and asking like if it is going to be a very big, huge alcohol group, I mean an OH group, will it not bring down the energy more?
So if you see the effect of say replacing this water with isopropanol, the reduction in energy is about 3 kilocalories per mole, and as you increase this group, I would expect this number to plateau out. So it won't be like 47 to 37 to 35 to eventually 0 as the group becomes larger. So for example, if I have to imagine the space as an actual spatial molecule, so a molecule with atom right here might not have as much effect on this reaction as the one that's right here. So if I say increase from isopropanol to say butanol or pentanol or hexanol, I would probably expect it to reduce by another couple of kilocalories per mole, but not dramatically. Does that make sense?
I hope so. I think the student will, because I think I would add, it's not like just the size, because for the molecules to actually repair it also needs to surge. So there is an amount of energy, or the steric hindrance will also come to play as we keep on increasing the size, right? So I think that will pick up.
That is correct. And the other thing is, some interestingly, some of these molecules are oriented in a very favorable way because of the hydrogen bonding that I mentioned in the first slide. So since you have a lot of OH groups, you can have an attraction between the hydrogen and oxygen molecule at any given location, making it uh, entropically a lot more feasible compared to other scenarios.
Right. Yeah. So there's one more question on possibly like if we like say instead of biomass, like if we talk about now extending the same logic, I mean the concept to waste tire, like how about this kinetic analysis? So this is a question from Dr. Rangabasham. So that means instead of like biomass pyrolysis, now if we talk about pyrolysis of like say waste tires.
Okay.
Vehicle tires. So in that case, can we follow a similar concept?
So when it comes to tires, what I know from working in industry is tires is similar to plants. It's one complicated mess. So it has several different components in it. It has inorganic compounds in it, like sulfur and other inorganic metals like iron and stuff in tires. You also have mostly hydrocarbons, aromatic and aliphatic hydrocarbons, because it's a styrene, butadiene polymer, isoprene styrene polymers. That's the constituent of tire. So now, when you think of the extension of this particular work, so so tires has a lot more of carbon instead of oxygen. So oxygen is kind of a no for tires. So you don't want oxygen molecules being used for making your tires. So a lot of this chemistry directly would not be applicable, but nevertheless, your free radical chemistries and your other 6-membered concerted reaction chemistries will come into play, and those all would have different types of chemical reactions than the ones that I've discussed here.
Okay, yeah. Thank you. So this is one question, a slightly little not technical, but because now there are more students, I just want to ask this question, assuming that I'm a student. So you have transacted from absorption, sorry, in your undergraduate to, if I see in your CV, it is process control kind of work with Professor Kaisere, and then again to biomass to in your PhD, and then after PhD is again transition to company working on lot more heat transfer fluids, polymerization, data analytics, software, and lot of tools. So I just want you to give your kind of an overall advice to the current students, because many of the students typically think if you do a PhD, you need to end up in academia or you have to become a teacher. That's not. And industry also requires very high qualified people to take up the application, or as a society itself, to the next level. So I just want you to give an advice to the current students how they should place their own aspirations of taking up higher education and the skill sets that they should develop over a period of years as they move from their undergraduate, and if they want to see themselves in industry down the line.
Okay, so I mean, this might be a lecture talk in itself, but I'll try my level best to do justice to this question. So the first thing I would advise students is to be open to learning. So if you look at the transitions I've made in my career from undergrad to master's to PhD, it would be seemingly disjoint research fields. In undergrad, I worked with Dr. Punuswamy to understand adsorption chemistry. And then in masters, when I was working with Dr. Nikhil Kesari. It was trying to understand microkinetic modeling. So it was in micro reactors and whatnot. And so there was a slight connection between my master's and PhD, but I didn't expect to learn so much chemistry in my PhD. I was thinking, I was imagining fluid mechanics, heat transfer, process control, but I would say this is the advice that my master's thesis advisor gave me. So, however, I should not say dumb. However slow learner you are, or so, if you put in the work, if you are a consistent 16 hours a day effort, no matter what, you would see fruits to that. And as far as learning new things, the way I would go into that is first assimilate the jargon in that research field. So for example, whatever work I presented didn't happen in like 6 months. I mean, it took 5 years to, and for the first 3-4 years, I pretty much had nothing in my, I was just trying to build enough expertise in this area to kind of understand what's going on and how to make some impact in this field. So it takes time. So you should not, for students here, I would say don't expect instant gratification. It takes a lot of learning and a lot of effort. If you are curious, listen to one of Rahul Dravid's commencement speech in YouTube. So he says, so undergrad or grad school is like a bamboo shoot, Chinese bamboo. So when you plant the Chinese bamboo, it takes about 6 years for it to even show up as a tree. And after the 6th year, you can actually watch it grow by the day. It will grow like a few inches like every minute or so. So it really took 6 years for it to grow, but from the outside, it might seem like it's just 1 year. So I would say put your effort and don't expect instant gratification from what, and try to understand. So especially for students, right? So when I was at Sastra or IIT or so, I didn't really study to become topper. I mean, I wanted to understand how thermodynamics works and how different topics in chemical engineering are, and try to understand what is going on in there. So it's like the quote in Bhagavad Gita. So right, so you need to not run after results. You need to run after what you would what kind of knowledge you'd gain from it, and results would automatically show. So that would be my 2 cents for students here. So and no matter what, keep learning new things. Don't I mean, just because it's a different field, it doesn't mean you should not learn it. So don't say no to any kind of knowledge that's coming your way. And with the way science is going right now, so probably 30 years ago, chemical engineering research would not have this. This would be something that a person in chemistry department would be doing, and not in chemical engineering or biotechnology or biomolecular engineering. Now these fields have gotten combined, and they are so close to each other that you can work on any different problem and it will still be in the same purview. And one of the other professors whom I worked with said, problems do not come with a name attached to it, so it wouldn't come in as like chemical engineering problem or a chemistry problem. So it comes as a problem, and you figure out a way to tackle it.
Yes, so. Yes, that's a perfectly nice, Dr. Vikram. I'm very happy. Rather, I want to iterate that you said, I think 16 hours, right? 1-6. So I just want to make sure that the students got it as a 16 hours. And the other thing is, you said it is assimilate the jargon. You didn't say, I mean, this is to the students, that you didn't say that as an use the jargon, but you said rather assimilate the jargon. So which means we need to understand the words that we use inside out. So this is the second most point which I want to reiterate to the students here. And obviously, as you said, don't look for instant gratification. The glory comes on its own for the person who is focused. Now, before I just close and give, I would just request one of your another faculty is also here. He joined little apart, so I could not ask him at the beginning. So, Dr. Rajan. Yes.
Yeah.
Yeah. So I just request Dr. Rajan to just give.
Yeah. So it has been a very long time, seeing Dr. Vikram.
Yeah.
I think last time we met in IIT Madras campus probably.
Yeah.
Yeah. Right. Okay. Very nice. Very nice. Sorry, I had another meeting, so I came only midway through your talk.
No problem. I really appreciate you joining this talk, sir.
In fact, I wanted to join from the beginning itself. Since the scheduled meeting got postponed, so it also trickled into the lecture as well, right? And I am very happy and also feel very proud. And actually, you lived to the words that you spoke. Like as an undergrad student, we had seen you staying with us till 10 o'clock, 11 o'clock in the night, as long as we stay, and the curiosity to learn, right, irrespective of the benefits that you derive, right? So that's something we appreciate a lot, and hopefully the subsequent batches or the students who are in the audience also get that message. Learning is important. Results come their own way. We don't have to really chase after the results. They come, right? Yeah, very nice seeing.
And I reminisce the times when Rajan sir would be actually on the back lab. There's a shed on the back where he conducts fluidization experiments. I would be on the other side. So we'll both go and have. So I think it was called Krishna Canteen or something like that. I don't know if it's still there. So we'd go have a dosa, come back and restart our experiments till like 11 o'clock. So he'll drop me off in the hostel. So it was fun times during then. I still reminisce those times there.
Yeah. So, you should, Vikram, you should tell it is 11 at the night. So otherwise, students will think it is the morning. So to the students, the time zone that they are talking is in the evening time zones.
Normally, our work used to happen only after the classes get over. So we normally start only after 5 o'clock or something like that, and go late in the night.
Right.
So really nice.
Right. Yeah. So I'm very happy. Let me just give a formal vote of thanks, Dr. Vikram. So I'm very happy to have you at the chemical lecture series for having shared. Indeed, you have shown that a chemical engineer is very transformational in nature in terms of the abilities a chemical engineer develops. He can work in all possible fields. As said, problems don't have a title attached to it. We just see the problem as a problem and bring in our own expertise and experience to it. I'm sure the students are benefited of today's talk, and you would probably get a lot of emails asking them for tips for higher education and also for how to join industry. I thank the Dean, Dr. Rajan, my Associate Dean colleague, Dr. Ponduswamy, Dr. Rangabashyam, the coordinator, Dr. Aragasan, Saravanan sir, and other faculty members and students who joined today's talk. Thank you all for this. We will meet yet another in a talk in a fortnight on such a panel. Thank you all.
Thank you very much for inviting me. And if there is a future opportunity where I can contribute, I would be glad to do that. Really appreciate the opportunity given to me. Thank you.
Yeah. Right. Yeah.
Thanks, Vikram. Thank you.
Thank you.
Yeah. Okay. Like myself and Vikram, Vikram, last year we had